Hello, class. In this lesson, we are going to cover equilibrium expressions. We're going to look at how to set them up. We're going to look at how to calculate them or calculate K given a set of equilibrium concentrations. And we are also going to interpret the value of K, our equilibrium constant. In order to do this, we're going to use the equation editor. So on Google Docs, if you click Insert and go to Equations, it opens up a toolbar. On this toolbar, we'll make use of some of the mathematical functions. We'll also make use of the fraction bar, and then you can do superscripts, which x to the b is a superscript, b is your superscript, or x sub a is your subscript. We're going to use both of those tools. Okay? So first, we need to figure out what an equilibrium expression is. An equilibrium expression allows us to express the equilibrium position of a reaction in mathematical terms. You'll see the terminology KEQ or maybe even KC for equilibrium expressions. I guess I should add in here KC refers to equilibrium concentrations, and Kp refers to equilibrium pressures. Since they primarily express pressures and concentrations, we can only determine concentrations of aqueous solutions and gases. Therefore, solids and liquids do not appear in our equilibrium expression. The equilibrium expression shows the ratio of concentrations of products to reactants. Since it is a ratio, we're going to be setting up a fraction. So I've got KEQ, my equilibrium expression for my equation. I'll click New Equation, and I'm going to start off with a fraction. On the top of my fraction are my products. In this generic reaction, I've got two reactants, capital A and capital B, and two products, capital C, capital D. The lowercase letters A, B, C, D are the coefficients, and we do need to account for those in our equilibrium expressions. That way, the rates of appearance of products and the rates of disappearance of reactants will be proportional to each other. The coefficients keep the reaction balanced, so we need to account for them in our equilibrium expression. So I open my bracket, and I have C. And then before I close my bracket, I need to put x to the b. I will close my bracket and press the right arrow key over 1, and you'll see the tick mark moves up to the right, so that way I can do my exponent. My exponent in this case is my coefficient, which is C. I can press the right arrow key again, and it puts me back on a normal line, and I can repeat the process. Open bracket, product D, close bracket, arrow, right arrow to go up to the D. If I press the right arrow again twice, it puts me on the bottom. And I can repeat this process for my reactants A and B. So what I've done here is created a generic equilibrium expression where I have the concentration of, product C in brackets raised to the lowercase c power, which is the coefficient. That's being multiplied by the concentration of D, my other product, raised to the D power, which is again tied to my coefficient. On the reactants, on the denominator of my KEQ expression, I've got concentration of A raised to the coefficient of A, and the concentration of B raised to the coefficient of B. Let's try to do a couple more examples. Here, I need to first identify what state of matter I have. All of these are gases. Therefore, they would all be included in my equilibrium expression. So since all of them are included in my equilibrium expression, it's actually the same as the one that I just started with. Let's go on to number 2. In number 2, A is a liquid. I will not include that in my expression. B is a gas, so I do need to include that. C is a solid, so I will not include that. And D is a gas, so I will include that. I could copy my original one and edit from there. I said I need to take out C because that is a solid. I need to take out A. The best way to get there is using the arrow keys. So left and right arrow keys. The equilibrium expression for this reaction would be the concentration of D raised to the D power over the concentration of B raised to the B power. Let's try the next one. In this next reaction, I have A, which is a solid. I don't have a B, so I can go ahead and get rid of B. I have C, which is a gas, and D, which is a gas. I do need to include my gases, but A is a solid, so that goes away. Well, I still have to have a denominator in my expression. So C to the C power times D to the D power divided by 1 maintains the same expression. I could then say that that is equal to, and then I would do, concentration of C raised to the C power times D, concentration of D raised to the D power. So this would be my final answer for this particular problem. Similar scenario here. Oops, didn't mean to take an entire screenshot. Similar scenario here for number 4. A is a solid, so that will not be in my expression. C is a solid, so that will not be in my expression. And I don't have any D, so I must put a 1 in the numerator. B is a gas, and that can stay in the denominator. There's no way to simplify this one, so the equilibrium expression for this reaction is 1 over B, and that's it. Now we've done it a couple times with generic equations. Let's try it with some actual chemicals in here. So I've got KQ. Maybe I should make this a little bit larger. I have N2 plus 3 moles of H2, and that forms 2 moles of NH3. So I do products over reactants. I see that all of these are gases. So I go N. If I'm keeping track of my subscripts, I need to use that X sub A button and then the right arrow over. You see it gets smaller, so I can put H3. Right arrow over again to make cursor normal sized. And then I need an exponent on this one. So I got to go back to X raised to the B, move up. Now instead of B, this time I'm going to use the coefficient, which is 2. So the concentration of NH3 squared is in the numerator. I do the right arrow over again to get to the denominator. And now I have the concentration of my reactants, N2. There is no coefficient listed for N2, so we assume the coefficient is 1. Anything raised to the 1 power is itself, so I don't need to write a coefficient for N2. But I do need to write a coefficient for H2. So here's H. Remember, right arrow over to get the small one. Play around with it and you'll get some practice. And this is to the 3rd power because the coefficient is This is the equilibrium expression for this particular reaction. NH3 squared divided by N2 times H2 cubed. So now I'm going to show you how to calculate K if I'm given equilibrium concentrations. At equilibrium, the concentration of N2 is 0.45 molar, the concentration of H2 is 0.12 molar, and the concentration of NH3 is 0.800 molar. So I need to plug those numbers in, products over reactants. So I'll do my fraction again. 0.800, and I know that's going to have to be squared. And then in the denominator, I'm going to have 0.045 molar for N2, and I should put my units in here. I'm going to go back and do that. And then that's going to be times the concentration of H2 to the third power. Now, order of operations, I need to take care of my exponents first. All right, so I'm going to grab my calculator. In my calculator, 0.800 squared is 0.64. We got 0.12, 0.12 cubed, that is 0.64, or sorry, 0.001728. And then next order of operations, I take care of the multiplication before the division. So I need to multiply this by 0.45, which is my concentration of N2, and I get a really small number. So then I do products over reactants. That's my last division part. 0.64 divided by, I'm going to do second answer to include that whole answer there. I end up with a very large number, 823. 823 is my K value. This is referred to as the equilibrium constant for this particular reaction. So the value of KEQ tells us the direction the reaction favors. If K is greater than 1, the products will be favored and the reaction proceeds in the forward direction. If K is less than 1, the reactants are favored and the reaction proceeds in the reverse direction. As you saw in some of our simulations, when K is equal to Q, that means the reaction is at equilibrium. Q is a very similar idea linked to concentrations, but Q can be used for any point during the reaction where K is only at equilibrium. You can only use equilibrium concentrations in a KQ expression. Whereas Q, which is referred to as the reaction quotient, you can use any concentrations at any point in time. So it says, let's interpret the value that we calculated. The value 823 is very, very large and much greater than 1. Therefore, products are favored. The forward reaction is favored. That means this reaction goes far to the right, and we produce a lot of NH3, and we have very little N2 and H2 left at equilibrium. All right. There are some practice problems here where you can go through and set up your equilibrium expressions. You can write them on paper and then upload them to the Google Doc, or you can use this equation editor. You have to interpret the value of some different K constants that are given to you, and then you also will have to plug in to an expression like this and solve and calculate a K constant or two. That is all for this lesson.